Let's have a look at solutions to our logistical model for population growth. Remember, this was the model where we have a natural growth rate and a carrying capacity, and the effect of this differential equation is to give us two equilibria, one at 0 and one at k, the carrying capacity, and it makes it so that when p is small, this differential equation looks approximately like R times P, which would be normal unconstrained population growth. So we solved this explicitly to get this formula for P, so let's see what graphs of this actually look like. Of course, to generate graphs, we're going to actually have to pick values for K, A, and R. So for these, I have sliders for A, K, and R right here. Currently, with A being 0, it turns out that gives us our equilibrium solution at the carrying capacity. You can see the carrying capacity is 10, and here this solution just stays at 10. Up here is the formula for this solution. To keep GeoGebra happy, I have to use the variable x instead of t. All right, so if we change k, of course that just changes where this equilibrium at the carrying capacity actually is. R is the growth rate, and since this population isn't changing, right now changing R won't change anything, so let's change A. Remember, A came from the constant of integration when we solved the differential equation, and so A is determined by the initial condition. Now we don't always have A equal to the initial condition. So we can't actually expect that A will be equal to whatever this y-intercept is. And indeed, right now, A is not equal to the vertical intercept here. But changing A will change what this intercept is and change the rest of the solution as well. So let's make A a little bit positive and see what happens. So for positive values of A, it looks like these are corresponding to initial populations that are above the carrying capacity. And as you would expect by the term carrying capacity, if the population is bigger than the carrying capacity, then the population starts to die off back towards the carrying capacity. And that's what we expected from the phase portrait that we drew when we developed this differential equation. So it's good to see that actually happening. You might think that this graph looks like a hyperbola, but it's actually not a hyperbola. It can't be because of the exponentiation that's happening. So that's what happens for positive values of A. We get these solutions that die off towards the carrying capacity. Now, if for a positive value of A, if we increase the growth rate, if the growth rate increases, then that should make us go towards the carrying capacity faster. And it's not totally intuitive why that should be the case, but it's an outcome. Since R is really controlling how fast any change happens, increasing R pushes you towards the carrying capacity faster. Okay, now let's see what happens when we have negative A values. So for negative A values, these are initial populations between 0 and the carrying capacity. And as you would expect, sort of given the phase portrait for the differential equation, populations that start between 0 and the carrying capacity, they do grow towards the carrying capacity, but as they approach the carrying capacity, they slow down so that they grow less and less fast. It turns out that they never actually reach the carrying capacity exactly, but they do approach it asymptotically. Of course, changing the carrying capacity just increases where that asymptote is. Increasing the growth rate, of course, pushes you towards the carrying capacity faster because increasing the growth rate increases how rapidly the population reproduces, and so you increase faster. All right, so these are basically all of the possibilities for what can happen with this logistic population growth model. This is a pretty common growth model for many situations, but there are some other things you could add to the differential equation often, in some situations, having this extra term here be linear is undesirable for various reasons, and so sometimes it gets replaced with a logarithmic model. Another thing you can do with this sort of differential equation is add the effect of predation. Predation takes the form of a negative term, so you might have some predators that eat whatever this population is, a deer or something. And you could just add a constant to represent a constant rate of predation. Of course, if you wanted your predation to be proportional to the size of the predator population, well, then you'd need a whole other differential equation to describe your predators.